Okay, so this is going to be a series of two sort of special lectures about minimal surfaces. So this will be instead of lecture 11 and 12 in the differential geometry course because Professor Arezzo is away. So we'll be replacing him. And so normally we have one lecture about this in this course, but now you will have a privilege of hearing me talk 2 times 90 minutes about minimal surfaces. And this should be a good thing, because minimal surfaces is actually not just, as you have heard so far, it's about mean curvature 0, and you can construct them in various very fascinating ways, like you can use soap films and wires, and what you get is minimal surfaces. I think that Claudio has said this. But it's actually also in pure mathematics today a very, very hot topic of research. So it is a topic with a lot of history. It started in the mid-18th century, and it is something that is still going on today. So if you want to really study something in differential geometry that is both very beautiful but also very useful, then this is one of those topics, at the very least. And so before we start, and I teach you what happened for the past 250 years, or at least start telling you parts of it, I just want us to think just for 1 minute about how difficult these problems are, because they are very easy to state, but if you don't know the mathematics, if you don't already have somebody telling you about the solution, then things are not obvious at all. But you might miss this if I just tell you everything and then you start thinking. So minimal surfaces are about, so the definition is that the mean curvature is 0, but they came to be studied in the mid-18th century by people like Lagrange and so on, because they were interested in the problem of area minimizing surfaces. So they were looking, so given some kind of boundary that is fixed, what is the surface that spans this boundary, so that has this boundary, this curve as a boundary, that has the minimal area? And this might seem like it's maybe not such a hard problem at first sight, but actually it is something that is not obvious at all. So first of all, if you just take something in a plane, if I take some curve in a plane, so planar, then you will have a planar surface that minimizes it. It will be just a plane. This is obvious. But if I take some complicated curve in all 3 dimensions, like this, then what will be the surface of minimal area spanning this? So imagine some wire that I dip in this soap film, again, if you've all seen this. Then it curves in various ways, and it is not at all obvious how it will curve or why. So this you can try to understand mathematically, but just as if I give you this problem and we pretend that it was now mid-18th century, this would not be something that you would solve in just one afternoon, most probably. And even this very simple example, let me ask you, so just imagine a cylinder in space. So what is the boundary of this cylinder? It has the 2 boundary circles, the one on top and the one on the bottom. And so is this a minimal surface? Does this minimize area? If I ask you such a simple question, so what happens if I deform this cylinder a little bit so that the circles are still a boundary? Maybe I push it in a bit on the middle, or I drag it out a bit on the middle. Even this, when you just think about it naively, is it obvious if the area gets bigger or smaller if you push it in certain ways? So what do you think? I mean, is this a minimal surface? Is this the optimal way if you have a cylinder? So who thinks it is?
But what is the curve we have?
So I will tell you all the precise definitions soon, but just naively.
What is the curve we are trying to find the minimal surface?
So you have the cylinder with the boundary circles, the one on top and the one on bottom. Okay? And then you want to deform it in a way so that these are still boundaries of a new surface you get. I will make it precise what it means to deform in a minute, but just naively, do you think if you push this cylinder a little bit, it will make the area larger, or it could make the area smaller, maybe, depending on how you do it? It could make it smaller, you think? Okay. And something, no. So actually, it is true that you can make the area smaller by pushing it, but this is already not obvious, I think, especially not rigorously proving it. And even if you do understand this and say it's clear you can make it smaller, then how do you make it smaller, and when do you stop? Like you don't maybe want to push it all the way in, or maybe you do, or maybe you stop at some point. Where do you stop, and why, and so on. I mean, all these questions you can understand mathematically, but just finding these examples, so this is the last thing I want to say before we start, that for 100 years, except for the plane, there were only 2 known examples. So all these great mathematicians were studying these problems, and we find 2 examples in 100 years. So now I will tell you during this lecture more than 2 examples, and you will say, oh, well, maybe it's not so hard. I give you the example and you check it. But, understanding these problems and finding it, it's not, today it's an exercise. Check if this is a minimal surface. But this is hard. So just so that you really appreciate the difficulty of these problems and sort of how hard it can be to understand these things. Okay, so enough with this talk. So let me get on with the lecture. And so since I'm not the usual lecturer in this course, I will just spend a few minutes on recalling the notation that I will use in case something is slightly different. I mean, I did my best to prepare the same notation as Locarno I follow essentially, which is the notation used by Claudio. But just in case my handwriting is different, let's get on with this. So let's go with notation. So for me, so we consider S a regular surface in R3. And in this lecture, I will always consider parametrized surfaces. And parametrizations I will write like this. So sometimes it's X underline, X overline, one of these bold face X's, but I will write it like this. Parametrization. From U, which is an open set in R2, into R3, and this sends the coordinates UV to X of UV, which is simply the vector X1 UV, X2 UV, X3 UV. Okay, so let's freeze this one. So this is, I think, standard notation. And then if you take a point in the surface, you have a tangent space, which is denoted TPS. And this has a basis. So the basis of this tangent space, standard one with respect to this parameterization, I denote by XU, XV, where these things are just the partial derivatives component-wise. So this is the first vector, and XV is exactly the same thing, but you take the derivative with respect to the second variable. Okay, so this is the notation that we use. Then you also have the unit normal vector, which I will denote by capital N. So I can also just quickly do the favor of doing a recap of the past 6 lectures in 5 minutes, so just to get all these notations in place. So this is the cross product of XU and XV, and then we normalize it, maybe length of this vector. This is the unit normal, and then you also have the coefficients of the first and second fundamental form. So all of this you have studied, and I call them capital EFG and EFG small letters. So with first fundamental form has the following coefficients. And the second fundamental form has these coefficients. So I take derivative twice, take the scalar product against the normal. So this is E. F once with respect to U, once with respect to V. And for G, it's the same as E, but with respect to E. Okay. So these are the things, and then we also note that all these expressions, they can also be written in another way. So this thing here is also equal to minus XU NU. Okay, so why is this? So this is because xu n. So if I take this scalar product, then this lies in the tangent space of S, and n is normal to the tangent space. So what will this be? Well, this will be 0, because we are orthogonal. And then you take then you differentiate this, and you get that x u n plus x u n u equals 0, and hence you move it to the other side, and you find that this one equals this one. And so in the same way, you can see that this thing equals xu and v, and it also equals xv and u, and this thing here equals xv and v. So with a minus sign. Okay, a minus sign. So you can also get these things, and this we will be using shortly. And then I should also recall to you, I mean, I'm sure that you have spoken about this for many, many hours very recently, but let me anyway recall that you can express very fundamental geometric quantities using only the coefficient of these forms. I mean, this is one of the points of introducing them. So let me remind you of the formula for the area. So an area, often a surface, it spans, I mean, it's an infinite surface. It goes to infinity. So when you talk about the area, you look at the bounded domain. So you let D inside U be some bounded domain. And you want to ask about the area of the part of the surface parameterized by this bounded domain. So you look at the bounded part of the surface and you ask for its area. And then the definition of this is that you integrate over D this xu, xv against du dv. I hope you will have seen this and remember this. And this you can actually write, this is a miracle, you can write it in terms of the coefficients of the first and second fundamental form in the following way. So we'll be using this. And then you also have mean curvature. So here you take, so at some point in the surface, so we'll recall to you the formula for mean curvature in terms of these coefficients. So you have seen these things? Good. So a formula for the mean curvature, so I will write it by h, and it is equal to EG minus 2 small f big F plus G times small e. You divide by 2 times EG minus f squared. So this is the formula for the mean curvature. Okay? So of course you have conceptually seen what this is. You look at the Gauss map, when you look at the differential of the Gauss map as a map from the tangent space of S to the tangent space of S. And then you take the, so minus 1/2 of the trace of the Gauss map, and this is the definition of a mean curvature. So you will have seen this, so I won't recall it. But then you can compute it in local coordinates using only these coefficients of the first and second fundamental form, and then you get this expression if you do the exercise properly. You will see that these things will be the same thing. Okay. So now let's get on with the definition. So are there any questions, by the way, so far at this point? No questions. Okay, that's good. It's clear. Okay, so let me also remind you that, okay, so x is regular if xu wedge xv, so at some point q, so this is non-zero for all q in u. Okay, so let me also remind you of this. So now I think I have recalled everything I need to recall to start with the actual lecture. So the definition of a minimal surface. So I said it has to do I mean, the historical origin of the problem is about minimizing area. But the definition is about mean curvature. So the definition is as follows. So a regular parametrized surface, so x from U to R3 is minimal if the mean curvature is 0. Okay, so let me just stress that this means that this H, I don't know, so of course this thing, it seems like it does not depend on P, but it depends on the point, right? All these coefficients depend on the tangent space in which you work and so on, so they all depend on the point. So if I was to call this H of P, then this has to vanish for all P. Okay, in X. So for all P, this is just something I want to stress. And then, just as a remark, so in case we don't work with a surface with a given parametrization, I can just say that the regular surface S in R3 is minimal if all of its parametrizations are minimal. Okay. So this is the definition of a minimal surface. And so what I want to explain next is its connection to this area minimizing problem. And so how should we go about talking about minimal area? And what exactly do we mean by this? So there are many ways in which we mean it. So let me just, as a motivation, let me just draw this cylinder again, of which I was speaking earlier. And I said that if we deform it a little bit, well, does the area get smaller, does it get larger, or so on? And this will precisely be the sense in which I mean that it minimizes area. But if I deform it in a nice enough way, smoothly, potentially, not keeping the boundary, but I will be precise mathematically about what it will mean, then I will get a change in area. I will be able to express the area all throughout this family of surfaces that I get, indexed by some time t, let's say. And then I will be able to find a critical point of this area functional. And then this critical point might be a minimum and it might not be, but we are looking for these critical points. So it is a variational problem. So it sort of lends some technique from this calculus of variation. And so what we will get is a surface that is called the catenoid, and it will actually look something like this. This will be the minimal surface. This will be the optimal thing. So I will go through this example in detail later. But just as a warning, so I tell you that it's connected to area minimizing, but actually, so this will give the minimal area of all these deformations where I push and pull in this way. But if I just said that, okay, I want a surface which has boundary, this circle, which has smaller area, then depending on the radius of this circle and the height of this cylinder, then you could actually just take the surface which is equal to the union of this circle and this circle. Nobody ever said here that the surface necessarily has to be connected. Okay. So there is this warning that sometimes you can find even smaller ones. But in a very natural sense, they are still locally area minimizing, so if you deform it, then it will be really the smallest one. So now let's go to the precise notion. So in order to state all this, I need to tell you what it means to to deform this surface in a certain way. And this is what is called normal variation of the surface. Okay, so the normal variation, what is it? So, okay, we are in this setting, so x is a regular parametrized surface, and we let D inside of U be a bounded domain. Okay, so it's a bounded domain. So this is what it will mean by local, right? So when I have a cylinder, it might stretch off to infinity, But when I talk about area minimizing, I cut it off at some point. And so this is my D will correspond to cutting off this surface. And I will look at this piece and say, how can I minimize the area within this D? Okay, and then I write my notation. So I write D bar would be just the closure of this circle. So it's D union the boundary D. So I will look at something closed, and then I will take H from D bar to R, a differentiable function. Okay, and this differentiable function will somehow decide exactly in what way I will deform this surface. Okay, so let's raise this. Give the definition of a normal variation. Okay, so definition 2. Oh, shit. So the normal variation of this surface, so which is x of d bar. So you see what this means. You take this bounded closed domain in here, and I look at the image of the surface I get. So x of d bar determined by the function h is the map.
Just have a question.
Yes.
Are we guaranteeing that the boundary of D itself in U?
That the boundary of D is in U, yes, we take it inside. So U is an open set, yes, and then you take an open set inside, which is bounded, and then the D bar should be in U. Yeah. So that's a good point. So it's the map phi from D bar cross minus epsilon into R3 given by phi of UV, and then I have the parameter T, which lives here, so UV lives here, and minus T lives in minus epsilon. So this is given by x of UV. So this was our usual parameterization, and then I will add something that depends on T, which will deform the surface. So plus T H of UV, N of UV, where N is the normal vector. Okay? So I will deform it in the sense of the normal vector. So let's see here. Here I have a normal vector, okay, pointing inwards or outwards depending on your orientation of the surface. Okay? So I have N, and then I will move in the direction of this surface, but times this H of UV. So I mean, maybe this is just 1 or minus 1, then we will just move in the direction of the normal. But maybe it's some complicated function, and you will deform it in a very complicated way. But so this is the definition of a normal variation. So of course, everywhere here, UV and D bar, and T is a minus epsilon. Okay, and so remark, so note, that for each T, so for each T minus epsilon fixed, okay, each fixed T, then xt, you can consider xt from D to R3, defined by the terms UV to xt to phi of UV. Then this thing is a parameterized surface. Okay, so what this means is that I deform this thing. I start at t equals 0, and I have my original surface. Then for each t, in this minus epsilon, I will get a new surface, defined in this way. And then so of course, for the original surface, it has some area. And then I will want to compute, these geometric quantities, but in particular, I want to explain to you now the connection with area minimizing. So I will take interest in computing the area of each of these new surfaces, xt. So I have a family of surfaces, and I want to compute its area. Well, how do I do that? This will be about understanding. I will do something even better, like in particular against this. I will try to understand the coefficients of the fundamental forms for all these new surfaces xt. But let me just finish this. So what does this satisfy? So this xt derived by u. So if I look at this xt and derive it in this direction. So this is what is called xtu so far, okay, by definition. So this is equal to xu plus thnu plus thun. Okay, you see? You have phi of ubt is this. And then you differentiate it and you get exactly that. So this is clear. And the same thing here, so partial xt partial v, which is xt v, is equal to xu, xv, of course, plus thnv plus thvn. So you get these two equations. So you get this whole family of surfaces satisfying these two equations. And now we are already on our way to being able to compute the fundamental forms. So now we will denote by et with xtu, and so on. So we will have all these fundamental forms. So we'll denote by et, ft, gt, the coefficients of the first fundamental form. So if we compute this, then what do we get?
E plus.
We get E plus something, exactly. This is a very good point. Why not? E plus something that depends on t. E plus t times something, where actually what this something is also important, and you will see what this is. And then plus t squared times something where it is less important what this thing is. Okay, so what you get is xu, which, as you said, this is just E. Okay, so you get E, and then, so what are the coefficients that you get? So T, and you get H, so TH times what? So you have this thing times itself. So you get TH, and you get XU, NU, plus the same thing again. So plus xu and u. Let me write it like this. And then plus t squared. What is the coefficient of t squared? And you get t squared h squared nu and u plus t squared hu. Okay, so is this clear?
This one is xu and u and xu and u again?
Yeah, it's the same thing again. So I wrote it out because if you do the F1, you get, two different things here. So I wanted to write it this way. But what you note here, so you can see also the yellow, right? So this coefficient, it was E. Well, actually, so of course I forgot all the T here everywhere. So I should just put T, T, XT, NT is the normal, so everything here.
But the first one has.
No, sorry, yes. Yeah, you're right. I did not forget it. Yes, I'm just confused. So it's E. Okay, so this thing, my second point, what is this?
E small.
E small. Exactly. Minus E small. So this is minus E, and this is minus E. So what I guess is this is equal to E minus 2TH times small e, and then plus all of this thing here. So let me just write R of t, all of this, the rest here. So these are all the coefficients with t squared or higher. So this is the rest. So this is an important thing that we should remember. So in the same way, we can compute ft, we can compute gt. And so let me just summarize on the blackboard what you get. So the computations are exactly the same. And I already explained how you connect this to minus u when I did the summary earlier. So what you get is the following. So ET, so now I'm just copying the one I just wrote, THE plus R of t, let's call it R1 of t. Then you have FT is equal to F plus TH, minus 2THF plus R2 of t. Okay, so this is something very similar to this thing here. So this is t squared, h squared, nu and v plus t squared, hu, hv. Okay, so you can check this. And then you get gt. So of course, always E and G, they behave in exactly the same way. It's symmetric with respect to U and V. So what you get here is G minus 2TH small g plus R3 of t, where this thing is exactly what is written here, but you change U for V. Okay. So this way you get the T equation. Okay, and so now what do we want to do? Now we want to get an expression for the area of all of these surfaces that are normal variation of the initial surface.
Is there any kind of other kind of variations other than normal variation?
Yeah, I mean, there are many potential things that you can do, but this is really what you want to do for minimal surfaces. But of course, I mean, if you think yourself, okay, so how can I do this? I think it is very natural to do something like this. You want to deform continuously your surface, and this is a very natural definition of doing it. And on top of it, it has the, I mean, because you deform in this particular way, you have very nice expressions for all the fundamental forms. So perhaps this is why people a long time ago chose to, I mean, use this strategy and not another strategy. But certainly, I mean, in mathematics, you're always allowed to think for yourself, and you're always allowed to define new things. But to my knowledge, this is really the predominant way of doing it. Okay, so now we recall. Sorry. Yes.
This is parametrized.
Yes.
Like D, it seems like a row or something like that.
Yeah, I mean, it's definitely a family, a continuous family of surfaces. So if you wanted to make a video of this, you could certainly let t be time, and you could get some continuous deformation of these things. That would be the normal variation. Okay, so now recall. So first of all, that the mean curvature is equal to this thing. So EG minus 2FF plus GE over 2 times EG minus F squared. So we have this thing. And so because of this, hence, now we want to compute this ET, GT minus FT squared. Why do we want to compute this quantity? Well, you remember that the area is computed as the integral of the square root of this quantity. So we're interested in this quantity. And what is it? So of course, we have to multiply the things that we have here with each other and take the square of the f. So what do you get? First term, EG minus f squared. So first you get the term that you like to have. That was the initial area. Then you get minus 2th times EG minus 2ff plus GE. You can check this. Okay, so now that I wrote this should ring a bell. Okay, this looks like something you know. And then plus some R tilde of t, which is the remaining terms. So these are the terms t squared and t squared and higher. I mean, you get what I mean by that. Okay. Terms with t squared and higher. Okay, so this thing, And we will not care about these right now. And why don't we care about them? Well, we will want to take the derivative in t of this expression and then put t equals 0. And then it is clear that this thing, which is a polynomial, you need t squared and so on, you derive it, there are t left, you put it to 0, it will vanish. Okay, so we're interested in the first order variation of this expression. So what you get is EG minus f squared times 1 minus 2th EG minus 2ff plus GE divided by EG minus f squared. Okay, you get this expression. If you just plus, of course, always this plus r tilde t. Okay, so this remainder is just always there. And then this is equal to EG minus f squared times 1 minus 2t small h, which again, I remind you, it's our function, but we are deforming along, determines the deformation, times h. And plus r tilde out. Okay, so this is the important expression. This ET/GT minus FT squared, this thing that we want to know what it is in order to understand the area, the variation of area, it's given by this.
That means this explains how this is related to minimizing area? Because if H is
Absolutely. Yes. This is exactly the next point.
This is 1 minus 4 times pH.
1 minus 4, because this thing there's a 2. Right? So I think this is. You mean here? Yes. Yes, you're right. Great. Thank you. Okay. Oops. Okay. So now let us see what we get when we compute the area. So now the area A of t, so by A of t I denote the area of the surface xt. Okay, so area xt of this v bar. Okay. So this is equal to the integral over d bar of the square root of et gt minus ft squared du dv. Okay? But so, what is this equal to? It is equal to the integral over d bar of square root of 1 minus, so this is by the computation that we just made, this thing here, that's eg minus f squared du dv. Okay, so this is clear. And now, if epsilon is small enough.
Clear because we have r tilde.
Sorry?
We have r tilde.
Yes, we have r tilde still. That is true. Thank you. Okay, so plus. It is correct. It still matters.
No, not correct. Because we have. I think
Yes.
we can't distribute the square root because we have a sum.
Yeah, but either way, I mean, it is under the square. So, I mean, so let me write this. It's okay. So this thing. Okay, so this is it. Okay, now it is squared. Okay, like this. Do I put the square? Yes, put the square. Okay, so now look at this function.
And we are also missing the h.
The h, I lost it too. Now it's okay. So now this function here that is under the square root. So we have to be a little bit careful. So this thing here is this differentiable. Okay. So of course we might have some problems sometimes. But so what happens? So note with epsilon. So it's a small positive number, so it's small enough. Then A of t is differentiable for all t minus epsilon, epsilon. Okay, because then, I mean, this thing will not pose a problem. This deformation that we have will not be so large that it poses problems of differentiability of this function. Okay? And then, when it's differentiable, we can compute it. So, at t equals 0, we now get the following. So we get a prime of 0. We can just differentiate this and put t equals 0. And then what do we get? So then we should get the following. Check this. That this thing, so if epsilon is small enough, we can make this computation and we get this result. Okay? So this is then the equation.
Are we here allowed to differentiate under the integral?
Yes.
Why?
Why? So we have, so I mean this thing is differential. Everything is smooth. Everything is very nice. I mean as nice as possible. So I mean you can use any of your classical theorems. I mean this is not a very delicate situation. There is a square root. But if epsilon is small enough, I mean this, remember that this is not some weird thing. This is t squared times something smooth. I mean this is just a polynomial. So you're definitely allowed to differentiate under the integral sign. Okay, now then you get this equation here, which is then the equation, I mean, so, okay, this is the expression a prime of 0. And then, of course, we are interested in this, so a prime of 0 equals 0 is the equation for our stationary points of the area. Okay, so we vary this area with t, and then when we find t such as this is stationary, then we are done. Okay? So if we started at the surface where a prime of 0 equals 0, then we had a minimal. When we had a minimal point, we had a surface which minimizes the area. Okay? So is this clear? So now, which is exactly what your remark was 2 minutes ago, can we not use this then? I mean, we have the mean curvature in here. This was the whole point. So then we can now see the connection between vanishing mean curvature at each point and this area minimizing property. And now we will then have a precise formulation of what it means to minimize this area. So this will be proposition 1, or maybe it would deserve theorem. Let me write this proposition. So let x u into R3 be a regular parametrized surface. So I assume it's already parametrized, okay? Parametrized surface. And so everything will be as what we did. It's a d in u, the bounded domain in u. Okay, then this surface x is minimal if and only if a prime of 0, of course minimal, the definition was that the mean curvature is 0 at every point. So the mean curvature is 0 at every point, if and only if a prime of 0 equals 0 for all such d, so any d bounded domain inside U, okay, and all normal variations of x of d bar. So this means that for all such d inside U, and for all the choices of h, this small h, this function which we use to determine exactly how we flow our surface to a new surface. Okay? So for all such normal variations, this a prime is 0, if and only if h, big H between curvature is identically 0. Okay, so the proof is more or less immediate now that we have done this work. So the proof is as follows. So one direction is completely immediate. So the first direction, so assume that H is identically 0. So at every point of our surface, H vanishes. So this clearly implies that A prime of 0 equals 0. Why is that? Well, we put H equal to 0 here. For every point, I mean, this is the 0 function. So then, of course, this integral vanishes. So for every normal variation of x of d bar, for every, okay? So conversely, so how do we do it in the other direction?
Approximation, because this is true for all h.
Yes, this is true
for all h continuous differential functions. So by continuous differential functions, we can approximate some polynomials or like this. And in real analysis, there is some problems like if integral is some two functions. If fg is integral, if fg is equal to 0 for all f. So in this case, g is 0. Such kind of problems.
You can do the
Okay.
H.
Yeah, let's say that there is a more elementary way. Let's put it this way. So this proof is not hard. So all you have to do is, so you assume that this A prime of 0 is 0 everywhere.
Can't we just take h to be?
I'm going to show H is 0.
Yeah, we may choose h to make the integrand positive function.
So what we can do is that we can make a proof by contradiction. We can say assume that H, the mean curvature, is not 0 everywhere. So assume, I mean, this is going to be along the lines of what all of you said, right? So assume, for contradiction, that there exists a Q in our surface, so in our surface, let's go, so it's Q bar, such that H of Q, let me write it this way, is not 0. Okay, and then what do we want to show? We want to show that if this is not 0, then this is not 0 for all the normal variations. So we want to find a normal variation such that this is not 0. Okay? And so how do we find such a normal variation? So what does it mean to find a normal variation? So what we mean is that, okay, D is sort of already fixed here. So now we just want to pick our small h, this function, such that this is not 0 if we assume that the mean curvature is not 0 everywhere. So at one point, at least, where the mean curvature is not 0. So now we want this integral to be not 0.
It means that it doesn't vanish in our neighborhood, right?
Yeah, so exactly. So we want to use this neighborhood of this point Q, and then we want to, we have no idea what happens far away from Q, so we want to just put our small h to be 0 far away. Okay? So it is non-zero at some point, and then it should go down to 0 sufficiently fast so that this is still non-zero. Because we don't want things appearing that compensate for this non-zeroness.
But can't we choose small h to be the mean curvature in our chart?
Ah, yes. So this is an interesting remark. So I will come to this soon. So not quite yet, but there is an interesting thing that happens if you choose h to be. So a mean curvature is a number, right? So, but if you choose,
Just to make the integrand positive, non-negative. Because if it is non-negative, then the integral must be almost everywhere 0, and then because it is a continuous function, it must be identically 0.
yeah. But so far, the problem with choosing h equals h is that you don't know. So you know it's non-zero somewhere, but maybe it's +1, but maybe it's -1 somewhere else. Maybe it compensates. So you need to use a cutoff function at this point. So then choose h that goes from D to R such that so h of q, small h of q is equal to a mean curvature at q, and h equals 0, it's identically equal 0 on this x of d bar minus some let me write it maybe VQ for some VQ neighborhood of Q, which is sufficiently small. So I don't have to write it more precisely like this. You understand what it means. You can fill in the details. So we use such a cutoff function, so it's 0 away from it, and it's equal to big H here. And then A prime of 0 will be strictly less than 0. Why did I write this? So is there a sign thing? So let me just write it like this. So for the variation, so maybe not for all variations, but for this variation, and this is enough. The variation determined by H. And so, I mean, this is a contradiction to the statement that A prime of 0 equals 0 for all normal variations. Okay? And this finishes the proof. So I mean, assume that this is everywhere 0, but that this is not 0. So assume for contradiction that, so I should have written here, assume for contradiction that A prime of 0 is equal to 0 for all the normal variations, and that this is not 0. Then you do this and you get the contradiction. Okay. So this is the proof. So is this clear? I will make some remarks now. Okay. Okay. Erase this. So what this means, just in summary, so remarks. So 1. So any bounded region X of D bar of a minimal surface X of U is a critical point for the area of any normal variation of this X of D bar. Okay? So it's a critical point. But then warning, so critical point is not necessarily the same thing as a minimum, and it's not necessarily the same thing as some kind of global minimum, right? So it is a local
minimum or maximum we don't know.
Exactly. So yeah, so this is what I mean when I write critical point is not necessarily a minimum. I mean that, as you all know, you've studied calculus and so on, just having the derivative equal 0 is not necessarily a minimum. It can be a maximum, and various things.
By this remark, do you mean that if I take any part of the surface, I can make a normal variation which makes this 0?
So
the A dash?
no. So what I mean is that I mean sometimes when you do these things.
I mean the remark itself.
This one.
Ah, yeah.
Aha. Okay. So what was your question again?
So my question is, does this just mean that any part of the surface I can make, for any part of the surface I can make a normal variation which makes the A dash for this region 0?
So it means that if you take any part of the surface, if it's minimal, then however you move with a normal variation, then the area, so if it actually was minimal, then it actually always gets larger, and perhaps it was a maximum point, and then it always gets smaller. I mean, this is also the point of this. But it means that it is really a critical point of the area functional in the sense that no matter what direction you go in, you know, the area can only change in one way. You know. only get larger, or only get smaller, however you deform. So it's really an optimal shape of the surface in one way or another. Okay? But just this warning, because I mean it's called minimal surface, so it's easy to think that it's always minimal. But this is somehow a name that has stuck throughout history because we studied these problems. We want to find minimal area. And this is because, you know, in physics it's important. I mean, naturally, nature optimizes things, so you get minimal things. So you call it minimal surfaces. But mathematically, these things you might end up with some maximum, okay, just in theory. So this is just a warning. And then also a second remark. So this is connected to what you said. So well, let me skip this one. This is necessary. I will do it later. Yes. Okay. So I haven't given any examples yet. So in order to give proper examples, I will still have to state one more theorem. But let's just start just by sort of example 0, and then I will go and prove some proposition more, and then I will come up with more examples for you. Okay? So the first example of something minimal is, of course, that any plane in R3 is a minimal surface. Okay, and this is completely obvious because I mean you have the parametrization of the plane, so it's just linear. So A1 plus B1U plus C1B and so on. Okay, so what you get, if you take this vector and you differentiate twice, you get 0. So when you differentiate twice, with all of these things, you get 0. Okay, so this means that E equals F equals G equals 0. And so H is equal to, just even without calculating the coefficients of the first fundamental form, you immediately see this. And you say that okay, so this is, you can also see that this is not 0, okay? So you can see that this will be 0. Because with E and G, they will be something. I mean, this is just linear. So that this is 0 is completely true. Okay, and then the second example that you have already seen.
From 0 to 2. Really?
Sorry?
Example 0, example 2.
Oh, okay, why not? So, the helicoid. This is actually a minimal surface. So the plane is kind of obvious. Everybody can believe, you know, a plane minimizes area. But the helicoid, so this is incredibly, Carlos tried to teach me how to draw a helicoid yesterday, but it was not very successful. It was my fault. So. You all know what the helicoid looks like. It is this sort of spiral thing, right? So let me just draw it like that and leave it. So you know what it looks like, the helicoid. So the helicoid, I can write down the parametrization even if I can't draw it. So x u v is a hyperbolic sine cosine u a sine h v. So you have gone through this in detail. I believe with Claudio. So I will just remind you briefly. I will just say, okay, raise the helicoid. You have studied it in great detail. If you don't remember, go back to the other lecture, and then I will focus on the new examples, right? So you can just check or recall, if you have probably have done this calculation already, that E is equal to G, which is equal to a squared cosine hyperbolic squared v, and f is equal to 0. Okay, and then you can also compute I mean, you can compute explicitly, certainly. Also, the coefficients of the second fundamental form, and you can compute this. So, you can compute that h is equal to 0 by computing small e, small f, and small g. But soon, I mean, I will show you a way which is much better than this. So therefore, let me not compute small e, small f, and small g. But I will show you why it's enough to compute this in a second. Okay? So anyway, you can believe me because I know you have done this. Okay? So let me instead focus on the new example that you have. So example 2. So this is the main one. So now this is a new example. This is something called the catenoid that you have not seen before. And this is precisely the solution to the problem I asked you in the beginning of the cylinder. What is the optimal shapes that it can take to minimize area if you have these boundary circles as a boundary on each boundary domain? And the solution will be a catenoid. And what is the catenoid? It's a surface of rotation. Okay, so you have studied, I think, surface of rotation. So given by rotating the graph y equals, so a here is some fixed positive number. Okay. By rotating a cosine hyperbolic of z over a, and this is called a catenary, okay, around the z-axis, so the axis x equals y equals 0. Okay, so what does this look like? So actually the miracle, this is not a miracle, this is just very natural, it's not a surprise. If you take, in the real world, in nature, you take a heavy cable, okay, and you hang it from 2 points, then it will make some shape. I mean, it will not look like this, it will not look like this, it will look like this, in a certain way, and exactly this shape is catenary. So actually, catenary is some fancy word for cable, okay? And so this is why it's called catenary, because it's exactly the shape that you get from it. And when you rotate this shape of a catenary, of a cable, if you rotate it around an axis, you will get some kind of cylinder that is sort of slimmer around the waist. And this is minimal surface. And of course it is, it is a miracle, but it's not a miracle. It should be expected. But nature, of course, it ends up this way. Exactly because it is the most efficient one. And so this is a minimal surface. I mean, this is extremely fascinating, but it's also, very, very natural in some other sense. So here is my paper. So what you get, it looks like this. So this is the x-axis, y, z, and then you get the catenary. It will look, something like, okay, like what the cable would look like. And the distance here is a. And this one is symmetric around the y-axis. And then you rotate it this way, and you will get something that looks like this, and this will be the catenoid. Okay? And the parametrization of the catenoid and the parametrization of a catenoid is the following. So x of uv. So it looks very similar to the helicoid, and this is not a coincidence, as you might see not today but tomorrow, on Thursday. So this is cosine hyperbolic cos u, a cosine hyperbolic v, sine u, and then a v. Okay, so this is the surface of rotation that you get when you rotate this thing around the z-axis. So you see that every circle here you see that it has radius. So what does it become? A radius is a cosine hyperbolic of V. So if you stand here at height AV, the radius is then a cosine hyperbolic of V. Okay? So this is how this thing works. So then what you get, you can compute xu xv Okay, so you get this thing. By the way, I forgot to say, so where is u and v? So u here lies in 0 and 2 pi, and v lies in minus infinity to infinity. Okay? So it goes off to infinity, but u is in 0 and 2. Okay, so you can compute these things, and then you will get that E, which is, you know what it is, it's been this one, scalar product with itself, equals G equals A squared cosine hyperbolic squared of V, and F equals 0. And then in the same way, you can compute now the normal vector, you can take the cross product, you can compute the second derivatives with respect to xuu, xuv, xvv, and you can compute small e, small f, small g, you can multiply it all together, you can see h equals 0 by this formula that we have for h, in terms of all the coefficients. But again, I will not do that. Okay? I will just remark. So here, and for the helicoid, check that if I take xuu plus xvv, so I mean this is much easier than taking cross product and doing all those things, right? So I just compute this. Here once more. This is 0. Okay. So remember, for the helicoid and for the catenoid, both these were true. Equals g and f equals 0. And on top of it, for both of them, we'll have xuu plus xvv equals 0. Does anybody recognize what this looks like, by the way? This has a name if you study analysis. Exactly, it's just the Laplacian. And what are functions called that have 0 Laplacian? Harmonic. Exactly. So actually, there is a very nice, very deep connection. There's a very nice connection between minimal surfaces and harmonic functions. Okay, and to see this, you have to introduce something called isothermal coordinates. So I mean, I'm sure that you have spent a lot of time talking about sort of canonical ways of parameterizing, or particularly nice ways of parameterizing a curve or a surface. For curves, you just use the unit speed parametrization. For surfaces, what is a particularly nice parametrization? Well, the thing that I will tell you about now, which is called isothermal coordinates, is exactly one of those. So the definition is the following. Definition, I don't know what number, 2 or 3 or 3 probably. Okay, so definition 3. So a regular parameterized surface, so x to v, is said to be isothermal if, so E equals G and F equals 0. Okay, so exactly as in these examples. So this has some meaning. Let me just remark on it orally. I mean, this is not something that is sort of completely trivial, but this has some meaning. So if you have a parametrization like this, then these isothermal, so by the way, they are called like this because these are the level curves of the Laplacian. So this, if you were a physicist, the first thing that would come to mind is that these are the level curves of the solution of the heat equation. And so this means the sort of solutions along which the temperature is constant. So iso means same, isomorphism, same shape, and so on, right? So iso means same, and thermal means temperature. So same temperature. So these are the level curves of solutions to heat equation. This is why it's called isothermal. And it's also called, in some literatures, this is also called conformal. Okay? So Duchamp and a lot of people, isothermal is most commonly seen, so I use it as well. But it's also sometimes called conformal coordinates. And this means that, when you have something like this, it means that it actually preserves angles.
The same meaning in complex analysis?
Well, so you should not, I think you should think of it as separate things. Yes. Conformal and complex analysis does mean the same thing. I mean, it means that you have a holomorphic mapping, it preserves angles.
Yeah.
So in the sense, it's the same thing. But it does not mean it's a holomorphic
Okay.
mapping. Actually it does, but not in the obvious sense. I will talk about this next time, okay? To receive a precise interpretation. But so what this means is that it preserves angles. So if you have two curves in the parameter plane, and then you map them, and they have some angle between them, you map them into the surface, then if a parametrization satisfies these conditions, then the angles, when they are mapped into the surface by this parametrization, they will be preserved. Okay. So this is what it means. So this is something very natural. And the theorem is this. So this is a hard theorem. Well, it's a hard theorem where it's something coming from, TD or something a bit outside of this course, right? So you have to solve a partial differential equation. We will not do it, so actually this goes beyond the minimal surfaces. So every regular point P on S surface in R3 admits, well, it has a neighborhood, let me write it like this, has a neighborhood with a reparametrization in isothermal coordinates. Okay, so let me say it in words rather. So if you have a regular surface, then you can always reparametrize it so it has coordinates like this. But this is subtle, this is hard. I mean, we don't do this proof in Duchamp, for example. We don't do it in many books on minimal surface. So this is something that we will admit, and then we will use it. But I can just remark that, so if you have a surface, I mean, people study surfaces of less regularity. So if you have a C1 surface, then it is false. So it is not automatically true. But if it's sufficiently regular, then it is true. And if it's minimal, the proof is easier, but it's still too hard for this course. Okay? So, now, so remark. So if X isothermal, then it simplifies the expressions a lot for the area. Sorry, I'm not standing away. So for the area and for the mean curvature. So then the area is the integral, over a domain. It's just E. F equals 0, G equals E, take the square root, just E. And H is equal to 1/2 small e plus small g divided by E. So now everything becomes somehow simplified. And then we have this key lemma. So now that I told you this, I will do exactly the remark. But what is the connection with harmonic functions? I mean, I just told you there will be something. So the connections is following. So let X be a regular parametrized surface, as always. and assume X is isothermal. So, I mean, this is important. You have to assume that it's isothermal. Maybe you have a surface, I mean, that you could put isothermal coordinates on it, but it's not yet, then you have to change it. So then xuu plus xvv, this thing that is the Laplacian, is equal to 2 times lambda times boldface h. Okay, so this is a vector where h is equal to the mean curvature times the normal. The mean curvature is now a number times the normal vector. Okay? So this is a vector. So it's equal to this, where this is this, and lambda is equal to xu, so it's equal to e. Okay? It's equal to e and it's equal to g. But for some reason it is always written lambda. So let us use the wisdom of the literature and call it lambda. Okay. And so what does this mean? So moreover, x is minimal if and only if the coordinate functions, so the coordinate functions are harmonic. Okay, so this means precisely that, I mean, all this partial xk partial u squared plus partial squared xk partial d squared equals 0 for all k equals 1, 2, 3. So I mean x is equal to x1, x2, x3, this vector, and all these things are harmonic, which means the Laplacian vanishes for every one of these 3 coordinate functions. Okay? So this is what we need. And this last part follows immediately from this. Okay. So I wrote down the intermediate step. Okay, so I mean it is now 1/2 past, but we started late, so I think I have some more 15 minutes to tell you about the proof of this. So are there any questions about the statement of the lemma? Actually, maybe it will be clearer if you have something, if you see the proof. So proof. So my x being isothermal, h is identically equal to 0. Well, so h equal to 0 at some point, if and only if e plus g equal to 0 at the same point. Okay, so why is this? I mean, h is equal to this thing, but e is not 0. Okay? Because otherwise it would not be regular. E is xu, so it's not 0. So h equals 0 if and only if e plus g equal to 0. But what is e plus g? So e is equal to xuu n and g is equal to xuv n is equal to 0. Okay, this thing is multilinear. So this is the same thing as saying that xuu plus xuv n is equal to 0. Okay? So now we should see what can we say about these things. So clearly now, so point A here, so if xuu plus xvv is equal to 0, then this thing is equal to 0. Okay, so this means that h is equal to 0. So if this thing is harmonic, so this means harmonic, right? This is another way of writing this. I wrote it out like this just to be clear. So if this thing is harmonic, then h must vanish everywhere. This direction is clear. So what about the other direction? Okay, so this is okay. So what about the other direction? So now, conversely, so we want to assume that h equals 0 and show that then this thing here equals 0. But h equals 0, as we just remarked in the beginning here, is equivalent to this thing being 0. Okay, so we can assume h equals 0 means that this is 0. And we have to show that this equals 0 implies that actually this thing is 0. So a priori, of course, it's not in general true that if you have a scalar product of two vectors, it's 0, then actually the first vector is 0. This is false.
It means they
But
are in the same direction.
in this case, it is true, because exactly they are parallel vectors. So this would be the idea of the proof. This vector and the normal vector, they are parallel. So then, it will be true that this one has to be 0, because the normal vector is not 0. Okay? So conversely, show that x u plus x uv and equals 0 implies x u plus x uv equals 0. To do this, do what I said, show that it's parallel. So this is true. Because, so n is not 0, of course, and x u plus x uv is parallel to n. Okay, why? Indeed. Let us see why this is. So, of course, n is normal to the tangent plane. And the tangent plane is spanned by xu and xv. So it is enough to show that xuu plus xvd xu is equal to 0, and that the same thing against xv is equal to 0. Okay? So to show this, so if we compute this, then what is it? So then we have to use this trick that we used earlier also to get another expression of small e and small f and small g. We have to sometimes write these things as derivatives of some other
But we can always take one of the derivatives to the other with a minus sign. So we will get the same is equal to minus itself.
Yeah, I mean, okay, so let me write what it is. And it probably will be. So it is equal to 1/2 xu, xu, u. Okay, so this means that I take the derivative in the u direction of this scalar product. Okay, so it's equal to this plus xu, xv, v, and then minus xuv, xv. Okay, so this should hang on. This is true. Okay, and this is equal to 1/2 xu, so let me just write it and then we'll look at it. So xv u plus xu xv, and then here, important, there's a v. Okay? Don't forget it. So now, what is this thing? This thing here, this is equal to e minus g. And then you take then you differentiate along u, but this is equal to 0 by isochromality, okay? Because we had assumed, so all these things are only true if you have isothermal coordinates, because then this thing is equal to 0. So when you differentiate it, it's still 0. This thing, this is equal to f, which is equal to 0, again by isochromality. So when you differentiate it, it's still 0. So then you get that this whole thing is equal to 0. Isotromality.
This term, this second sum, where does it come from?
This one.
No. Yes, exactly.
Yes. I mean, so you should just write this out and see that it's true. So, I mean, if there's a mistake, then something like this is true. So, this is what you should do. Okay, and similarly, xuu plus xuu, xu. I did not do a very good job erasing this blackboard. Okay, so this thing here, sorry, against xv is equal to 0. Okay, and this means that indeed they have to be parallel, okay? Because it's parallel to any vector spanned also by xu and xv. So it's parallel to the tangent space. Okay, so hence this means that xuu plus xvv is equal to some constant times the normal vector, okay? Where c is some non-zero constant. But what is it? So this constant here, there's actually no choice, but actually this is equal to 2 lambda h. So you can check this. So y is equal to 2 lambda h. It is because if you write this thing as a constant times n, then this is this constant, then this constant times n is equal to this constant times the scalar product of n with itself, which is the unit normal, which is this constant. But then this thing has to be equal to 2 lambda h. And then this implies, so I mean, in the end we wanted to prove, so what did we want to prove? We wanted to prove that h was equal to 0 if, no, so, okay. So if h was equal to 0, then this thing is equal to 0. And so this implies this thing is equal to 0. Because if you take h equals to 0 here, I mean, this thing is equal to 2 lambda mean curvature times the normal. And so if the mean curvature is 0, then this thing is equal to 0. Okay. And so this finishes the proof. So there is one corollary that I would like to mention from this. So I will finish in 2 minutes. Okay? And so the corollary the following. So if I ask you, by the way, I told you that for 100 years, apart from a plane, only 2 examples were known. And these examples were the ones I told you about, the helicoid and the Catenary. Okay. But apart from this, not much was known. What is a minimal surface? And I mean, at this point in the class, also you do not have any more knowledge about how you can construct minimal surfaces, understand what is a minimal surface and what is not. If I give you a surface, I say, is it minimal? You can only check it. Say h is 0, h is not 0. But you cannot have a feeling for why or how you would come up with such an example. So we will see beautiful connections with complex analysis next time that allow us to do this. Okay? But the corollary here, yes?
If we have a harmonic function, so we can construct corresponding.
Yes. So it is based on this. So I mean, so if you can find, so if you have an isothermal parametrization of something, then it is minimal if and only if the coordinate functions are harmonic. So this is why when I told you, okay, we should check if the catenoid and the helicoid are harmonic, all I did was I said, okay, I computed E equals G and F equals 0. This means isothermal, we now know. So because it's isothermal, these parametrizations, the standard parametrizations of the helicoid and the catenoid, all we have to check is that xuu plus xvv equals 0, so that all the coordinate functions are harmonic. But this is easy, you just derive twice with respect to u, derive twice with respect to v, and you see that one vector is minus the other. Okay? This is not hard. This is very quick. And then, as you said, you can try to use this to guess at examples. But there are even better ways and very strikingly beautiful ways that we will see next time. But before we end, just let me tell you this corollary. So if I say something silly like, I ask you, is the sphere a minimal surface? Is the torus a minimal surface? Something like this. Maybe you have no idea, right? I don't know. Do you have any idea? The theorem is, the corollary of this is there are no compact, be bounded and closed minimal surfaces in R field. The sphere, bounded and closed. Torus, bounded and closed. Okay? So they are not minimal surfaces because there can be no compact minimal surfaces. So why is this?
Because of harmonic functions in compact, we don't have harmonic functions.
Exactly. Because of the maximum principle. Maximum principle. So the maximum principle for harmonic functions. So this is something that, I mean, we will not prove the maximum principle for harmonic functions, but this is something well known that exists. For harmonic functions, so this implies that any harmonic function on a compact must, any harmonic function anywhere will take its maximum value on the boundary. Okay? But now, for example, if you have something compact, it has no boundary. It is bounded and closed. So the sphere, what is the boundary of the sphere is the surface, it doesn't have any. Okay? This is important to understand. So it means that it has, any compact has an interior maximum, but then actually this harmonic function must be constant. So it is a bit like what you saw in complex analysis, right? It's not too different from these two. So the maximum principle for harmonic functions implies that each coordinate function x1 of uv, x2 of uv, x3 of uv is constant. But this is a contradiction. Because if you have a regular parametrized surface, which is just one point, it is not a regular parametrized surface. Okay. So this would be a contradiction. So along these lines, and you can have this, you can think of this as an exercise if you want to write it out for yourself, maybe check this maximum principle and so on. But so you can have no compact minimal surfaces. And minimal surfaces are kind of rare, so you know what the surface of revolution is. So this catenoid is the only surface of revolution that is minimal. Okay? And I don't think you know what the ruled surface is yet, but in case there's something called a ruled surface, in case you know. And the helicoid is the only example of a ruled surface, which is minimal. Okay? And if you have a graph defined, these surfaces that are graphs of functions. So if you have a graph defined over the whole plane, whole of R2, and you assume it's minimal, then actually it has to be a plane. So minimal surfaces are kind of rare. It's hard to find examples. They cannot be compact. But you can go along these lines. Now we have seen if you have isothermal coordinates, then if you have harmonic coordinate functions, then you get minimal surfaces. And in complex analysis, the real part of a holomorphic function and the imaginary part of a holomorphic function, they are harmonic functions. So actually you can use complex analysis to translate into this, and we will prove something very beautiful next time, which is about given holomorphic meromorphic functions satisfying certain properties, you can always construct a minimal surface. And this way you'll just be able to take any meromorphic holomorphic function satisfying these properties, and you will get beautiful minimal surfaces. And this is like a real beautiful point of this view. So this will be next time. So this ends the lecture for today, unless you have any questions.